Hello and welcome to my talk. My name is Eleen. I'm from Friedrich Schiller University in Jena, Germany. And today I'd like to show you how to integrate astronomy into the mathematics lessons without taking away valuable time from the math curriculum. And I'll begin by shortly telling you why I'm pursuing this approach. Here you see a map of Germany and its states, and the colors show you where and if astronomy is taught in school, in secondary school. And you only see 3 states that actually have it as a separate subject. The yellow states have it incorporated in part in the physics curriculum, and the red states don't teach anything about astronomy at all in school. Also, times change. In my state, Thuringia, the green one in the middle, just this year decided to eliminate the subject of astronomy and also incorporate it in other subjects. So there's not a lot of astronomy taught in Germany, and I'm afraid that's how it also is in other countries. So I thought there's a need to teach astronomy or to convey astronomical facts and laws in some other form. And I thought, well, math is a subject that is mandatory in every grade. So in math lessons, we have word problems or applied problems anyways that need a topic and a content. And I looked at 24 math textbooks and analyzed them and found out that astronomy so far is the least used topic at all. So I wanted to add to that to help the diversity of math problems and to convey something about the universe to school kids in Germany. So the goal is to use either a fact that's like a one-sentence truth, like moon moves away every year from Earth, or data or a whole data set, or a law, so a formula in the math problems that I'm going to create. And the topics, the astronomical topics I'm using for it are the ones you see here. In the top row, that's what I would call basic knowledge, because those are the contents that we would teach if astronomy were a subject in school. And the lower row are modern topics in astronomy that I would also like to incorporate in the math problems. Today, I'm going to show you 3 examples. It's going to be a colorful mix of everything that's possible. You see these 3 problems, they come from different branches of mathematics. 2 of them will be mostly closed problem. 1 will be an open problem. I have single work, group work, partner work. So yeah, gonna be fun to see. With the problems, I'm also creating sample solutions and a teacher's commentary. The teacher's commentary is to give more background information or to alleviate hesitation in using the problems for those teachers who are not specialized in astronomy. But today I'm only showing you examples. And for that, I'm going to switch my screens. All the examples that I'm going to show you today are for grades 5 and 6. So this is the first one called Traveling Through Space-Times, and it's about learning how to use a coordinate system. When I create the problems, I have to think about what do the pupils know prior about the astronomical topic and what is my goal of what do I want to convey. And space-time is a very deep and heavy topic, and those kids are only like 10 years old. So I decided in the introduction to only tell them that, you know, for physicists, space and time go together, they form a unit, and we have these cool coordinate systems that tell us how objects move in space and time. So nothing about relativity or Einstein. And then they have these boxes here that explain how to read the axis. So space shows us the location in space, and time is the time passed since the moment now. And we start with, of course, from, you know, we go from easy to more difficult. So we start with an easy exercise. We just have 3 locations given, and there's no movement. It's just time passing, and the kids need to draw the points like a couple of hours later into the coordinate system. Then the next step is adding the movement, the change of space. I'm not using the word world line here. I'm just explaining to the kids that, you know, as time passes, it creates a line. And when you move your location, it also creates a line. So the exercise that goes with it, the task that goes with it is we basically have a story here. We have locations given, and we have 4 friends. They're all together in house C now, and they have different journeys, and at the end some of them meet up, and the kids are supposed to draw it in the coordinate system. The third task, sub-problem, is an open problem, because now they know how the coordinate system works. They're supposed to write their own story, and there are again some houses and locations given. They can add as many people as they want to, and then they draw their own space-time diagram, read the story to the neighbor, and the neighbor checks if the diagram actually goes together with what the story tells. In the last subproblem, I teach them about how a point in the space-time diagram is an event, and I give them certain events, and then they have to find the events that are at the same location or at the same time or in the past or in the future of a certain event. So this is about the understanding of simultaneity of events or things occurring at the same location, and they need to understand, like, from a certain point, where is the past of it in the diagram and where is the future of it in the diagram. The next problem is about sunspots. And I might add here, the original worksheets are not as colorful. I've added some color for you to help the presentation and for you to follow me along more easily. Here in the introduction, I tell them about what a sunspot is. It's a dark spot on the surface of the sun, and it's an indicator for the sun's activity. And the activity is important because the activity of the sun has influence on us, on the Earth. And the goal here is to give them a feeling that the sun is ever changing, because here we work with real data, the average number of sunspots per month from different months and years. And here they should get a feeling for how the numbers change. They do some statistics with it, and then they're supposed to assess, like, what statistical value is best to judge the risk of a disturbance due to solar activity. In subproblem 2 here, they get a little historical fact, because here it tells them the monthly sunspot numbers were recorded since 1749. And in the third subproblem, again, they have some daily sunspot numbers given, and they have to do some statistics with it. And this subproblem teaches them that statistics can be easily manipulated by selectively choosing specific values or just specific times when you collect the data, and that it's very important for science to gather data daily, or in general, just to gather as much data as you can. And the fourth subproblem is a group work or a task for the whole class, actually, because here they are supposed to rediscover the Schwabe cycle. So the fluctuation in the yearly numbers of sunspots. And we have a lot of data for that starting in the year 1975. So that's why it's a task for the whole class. So each pupil can calculate with like 1 year. It doesn't have to do like 50 years by himself. And I'll show you the solution. When they calculated the mean average for the year, the mean arithmetic, they will get this nice diagram. So it's 4 Schwabe cycles, and they're supposed to calculate what is the arithmetic mean of the length of such a Schwabe cycle. And so they can they just count the years from maximum to maximum and or from minimum to minimum. And then they will end up with a result of it's 11.1 years, which is really funny because it's a great coincidence, but 11.1 is actually the overall average since sunspot numbers have been recorded, and that the last 4 cycles end up with exactly that value. It's kind of lucky. The last one is a rather short one. It's an open problem, and it's about geometry. It's about the robots on Mars, the rovers. And in the introduction, I tell them about the Mars rover, its curiosity or perseverance, and what their task was on the Mars, and what they found out. For example, Curiosity found out that, yes, there once was liquid water on Mars in lakes and rivers. And then this is the sheet for partner one with the Curiosity rover. They have this nice coloring picture here. It explains a little bit about the parts of the robots, and then they have to work with angles, types of angles, and estimate the size of angles. And I hope as they work with this sheet, they really come to appreciate the technological feat they represent, like having rovers on Mars, like gathering data on a different planet. That's quite an accomplishment for humankind, I think. So in the end, I would like to show you some feedback the pupils gave me, and I'm going to switch my screens again for that. So I took the problems that I had created and took them to schools and tried them out with pupils. All in all, I collected feedback from 185 students across grades 6 to 10. I'm going to show you the results of the ones from grade 6 here. They've got a little form they could express their opinions on using a scale. So it was very sweet and short for kids that age. So I first asked them how much they knew about the astronomical topic before they worked on the math problem. And this is the result of it. And then I asked, how much would you say you learned? And how much do you know now more about this topic? And here you can see the result of it. And what I expected was like, yeah, of course, the people who already know a lot, they're probably here. They know nothing more, right? So it should look like this. If you already know a lot, you cannot learn a lot more. If you know nothing, you can learn a lot more by solving this problem. But the actual results looked like this. That was kind of a surprise to me. No matter how high or low your prior knowledge was, there are always students who felt like they learned a lot, and always some who felt like they didn't learn like a lot. But most of them still learned something, and there's really only a few who said like, I already knew everything. I also asked them how interesting they found the astronomical topic, and I'm very glad that the majority said, yeah, that was interesting to me. And for me personally, the most important question was, well, compared to a typical math problem from a textbook, was it more interesting? Was it better? Was it worse? And 91% stated that compared to a traditional textbook problem, the developed problems were like equally or even better. So I'm really happy about this. And it really encouraged me to go on with my project. And I would like to encourage you also to try things like this out in your country and in your schools. If you have any more questions about it, you can ask me today, and you can also write me an email to this address. Also, if you would like to receive the problems, the worksheets, then you can also write me in this address. Thank you so much for joining today.